separate objects of our intuition, of our thought. Also, we observed that a set should be well defined in the sense that given a set and given an element, the element should either, given a set and an object, the object should be either in the set or not. There should be no confusion regarding that. There should be no ambiguity regarding that. There should not be any boundary case. And also we take the members or the elements of the set as distinct. When we write a set, actually there are two methods of writing a set. One is called the roster method and the other is called the rule method or set builder method or property method. In the roster method, a set is expressed like this. You first put a opening curly bracket, then you put the names of the elements, say A, B, C, with commas between them, and then put a closing curly bracket. This is the way we write a set in the roster method. When we write sets in this way, the order in which we are writing the element is immaterial. That is, if a set contains elements A, B, and C, that can be written this way, or that can also be written in this way, or that can be written in this way. All these sets are one and the same. That is, the order in which the elements appear in the representation is immaterial. Another thing is that even suppose you write, you take this set A, B, C, and we also write it as A, B, C. Both the sets are one and the same, even if a particular element is repeated so many times. Actually, this is unnecessary. This is better because both contains the same information. So there is, it's always efficient to write an element only once, and that is usually the practice. So we write only the distinct elements. In fact, there is another concept called multiset, in which the same element can be repeated a finite number of times. There is the concept of a multiset. That is a different concept. In a set, that is not necessary. The elements are to be distinct. And the order in which the elements are written is immaterial. And suppose I call this set capital A. One convention is that the sets are all represented using capital letters, and the elements of the sets are written as lowercase letters, small letters. There is a convention. Actually, such conventions are very useful when you write and when you read mathematics. And most of the time people follow this kind of conventions. So that is the convention. The sets are to be given as the name as capital letters and the elements as small letters. Now, so suppose you take, so here B is an element of A, and that is written in this way: B, this symbol, and so let us B is an element of this. This symbol is similar to the Greek letter epsilon, but different. Usually, when we need the epsilon, the Greek letter epsilon in mathematics very frequently, especially in analysis. And when we write epsilon, we usually write it in this way, whereas element of is written in this way. So elements are also called members sometimes. Sometimes we may be writing a statement that something is not an element of the set. For example, I want to write X is not an element of the set A. That is represented like this. We put X, then we write this element of symbol, and then we put a slash like this, and then we write A. This means X is not an element of A. And using slashes to denote the negation of a relation is a practice. For example, suppose we write A divides B. A and B are integers. We write A divides B by using this vertical stroke. And suppose you want to write A does not divide B, we write this. So, not an element of, that is also written like this. And it should be kept in mind that a set containing only X and the element X are different. You cannot identify an object X with a set containing only that element. A set containing only one element is called a singleton. A set containing only called a singleton set. A set containing no element is called an empty set. A set containing we can write that a set A is a singleton set if for every xy in A, x is equal to 1. For every x, this means for every x element of A and for every x element of, for every y element of A. That is abbreviated as for every x and y in A. This for every is a very important symbol in mathematics. Usually, in order to write meaningful things precisely, in mathematics, a special notation is used, that of logic, symbolic logic, and this symbol is very important. I will discuss more about this later. So you can either write for every in English and better use this symbol. The point is that an object X and a set containing only one element X, these are to be distinguished. They are not one and the same. There is another, this roster method of representing a set is possible only if the set is finite and also if it contains only a few elements. If the set is big, even when the set is finite but it is very big, then this method is not feasible. So we will not be using that. So this roster method is feasible only for finite sets and even among finite sets for small sets which contain only a few elements. For very big finite sets or for infinite sets, this method is not feasible. For that we use another method that is called a rule method or set builder method or property method. For example, suppose we want to specify the set of all integers. So that is usually done in this way. We put first the opening curly bracket, then put X, then put a vertical line or a colon like this, and then write X is an integer. Then the closing curly bracket is put. The set of all integers. An object is an element of this set if and only if it is an integer. That is what it is. And sometimes people use X, then a vertical line, then X is an integer. This vertical line can be read as such that set of all X such that X is an integer. So here this X is an integer. X is an integer is a statement about X. By statement I mean a mathematical statement. And the assumption is that given any mathematical statement, that should be either true or false and not both. It is not any statement in the language, because a statement in the English language, for example, need not have this property. Suppose I clean this board and write the only statement on this board is false. I am cleaning the board, then I am writing the only statement on this board is false. That is a normal English statement. But it cannot be considered as a mathematical statement because we cannot assign any truth value for that. Suppose that statement is true. If that statement is true, then that statement is false. That is the content of that statement. The statement says that the statement is false. The only statement on this board is false. And suppose the statement is false, then what happens? Suppose the statement is false, that means the statement is true. So contradiction in any case. So that means we cannot assign any truth value for this statement. Either the truth value true or the truth value false. So that cannot be taken as a mathematical statement. So here, instead of this x is an integer, we can substitute by any statement. For example, I can write the set of all x such that x is a real number. Or the set of all x such that x is a mango. All these things are possible. So the most general form is something like this. Set of all x such that p of x, where p of x is a statement about x. Statement means that is either true or false and not both. Of course, there are similar other statements like the famous statement that all Cretans are liars. Crotona is an island near Italy, and somebody from that island is claiming that all Cretans are liars. The problem is that he himself is from Crotona. So if this statement is true, then that statement should be false also. And if the statement is false, then it is true also. So there are several such paradoxical statements. Another thing we should make sure is that this statement should not be ambiguous. For example, we cannot take the set of all x such that x is a tall human being, because there is no precise definition for a tall human being. If you give a precise definition, then there is no problem.
Is there any difference between preposition and statement?
By mathematical statement, we only claim this, that it should be either true or false and not both. Some other terminology is also used by some people. Some people call it the proposition. And there is something called the propositional logic. If possible, we will discuss such things later, because these things are essentially related to set theory. So I will be coming to that later. So in this way you can specify the sets, and in this way we can specify sets which are very large, and we can also specify infinite sets. For example, the set of all integers, the set of all real numbers, set of all rational numbers, etc. are all infinite sets. So for representing infinite sets, roster method is not feasible, and only rule method can be used. In the case of finite sets with very large number of elements, roster method is not feasible. We prefer rule method. And for sets with small elements, you can use either rule method or roster method. Now there are some small variations of the rule method like this. Suppose I write something like this. Suppose that A is the set of all x such that x is an integer. Then I want to write another statement B, that is the set of all x such that x is an element of A and x is greater than 0. A is the set of all integers. That is, I want to define another set B. B is the set of all integers or the set of all elements of A which are greater than 0. Or more generally, we may be defining sets like that. Set of all x is an element of A and a particular property holds. In this case, you can also as well write this as x element of A such that P of x. That is, this set can be written as the set of all x element of A such that x is positive. It's a small variation of the rule method. And sometimes, instead of writing x here, we may be writing something like this. For example, the set of all 2x where x is in integer. Actually here we are not writing x, instead of that we are writing a function of x. That is also possible. So you can write something like this, a function of x such that x is an element of some set. For example, in analytic geometry, suppose we want to specify the unit circle. Unit circle is the set of all points xy in R2 such that x square plus y square is equal to 1. So I can write it as set of all ordered pairs xy in R2 such that x square plus y square is equal to 1. These are all small variations of the rule method which we employ very frequently. So these are the two main methods of writing a set, representing a set. But of course, in some case we use other methods also. For example, a language is, suppose sigma is a finite set of symbols called the alphabet, then a language is actually a subset of sigma star, where sigma star is the collection of all finite sequences of symbols in sigma. So actually language is actually a subset of sigma star. And how to specify a language? In order to specify a language, we neither use roster method, because the language may contain several, a very large number or even infinite number of elements. So roster method is not possible. Even the rule method may not be helpful in representing a language. We use what we use? We use a grammar or a machine like deterministic finite acceptor or non-deterministic finite acceptor to represent a language. In fact, a language is a set. But in that context, rather than rule method and roster method, grammars and deterministic finite acceptor or non-deterministic finite acceptor are more convenient. There is a next question. The next question is, when do you say that two sets are equal? The rule is that two sets are equal if and only if they contain the same elements. Sets A and B are equal if they contain the same elements. That is, A is equal to B if and only if an element of A, if and only if X is an element of B. This symbol, this is if and only if, or implies and is implied by. This means that the statement to the left of that and the statement to the right of that are logically equivalent. If this is true, this is true. If this is true, this is true. That is, A, set A and B are equal if and only if whenever something is an element of A, it should be an element of B, and whenever something is an element of B, it should be an element of A also. That is a necessary and sufficient condition for two sets to be equal. Some people are abbreviating this as IFF. That is also common. And it is heard that this technique was introduced first by the famous textbook writer P.R. Halmos. In fact, it was he who introduced the symbol to denote the end of a proof. If you look at any mathematics book giving proof of theorems, after the completion of a theorem, sometimes you can see a symbol like this or something like this. A rectangle which is either filled or not filled. This was also introduced by P.R. Halmos, and somebody had called this the Halmos tomb. This similar to the tombstone. Actually, the earlier people used to write quat erat demonstrandum in order to say that the proof is over. Quat erat demonstrandum in Latin. And some people used to abbreviate this as QED. In some books you can see, after a proof it will be written QED. And actually this is a replacement for that. And this is more convenient than writing quat erat demonstrandum or or QED. Or some people write just hence the proof. So these two symbols are introduced by P.R. Halmos. Now I defined Now I have to define another concept, the concept of a subset of a set. Suppose A and B are sets. Then we say that A is a subset of B if every element of A is in. A set A is a subset of a set B if every element of A is in B. And we usually write this by the symbol read as A subset of B. Earlier, this notation was also popular for writing A subset of B. I think nowadays this is more preferred notation. So we use this notation. But in some books you can also see that this symbol is used for writing subset of. Formally, this means that A is a subset of B if X an element of A implies X an element of B. Now, what is the meaning of this implies? X is an element of A implies X is an element of B. This means that if X is an element of A, then X is an element of B. That is the meaning of this. For that, this arrow is used. In mathematics, we use several such statements. That is, more generally, we can write statement like suppose P is a statement and Q is a statement. We write P implies Q. This means that if P is true, then Q is true. If P is true, then Q is true. These kind of things are usually represented using truth tables. There's something like this. You can draw a table like this: P, Q, P implies Q. P can be either true or false. No other possibility. So P can be true. But when P is true, Q can be true or Q can be false. So one possibility is that P and Q are true. The other possibility is that P is true but Q is false. And another possibility is that P is false but Q is true. Another possibility is that both are false. So P takes 2 values, Q takes 2 values, altogether P and Q takes 4 values. So these are the, then under these circumstances, what happens to the statement P implies Q? P implies Q only states that if P is true, then Q is true. If P is false, we are not telling anything. If P is false, Q can be true or false. We don't know. The only thing we are asserting is that if P is true, then Q is true. If P is true, then Q is true. That means P is true, Q is true, this is true. And P is true, Q is false. That is not possible because if P is true, Q should also be true. So this is false. And if P is false, we need not look at the value of truth value of Q. It is true in any case. So these two are things. You can understand this by looking at this. I did this in the way. That is, when is P implies Q false? Because most of the time P implies Q is true. In all, there are 4 cases. Of the 4 cases, in all the 3 cases, P implies Q is true. So what is the only case where P implies Q is false? That is only when P is true and Q is false. In that case, the statement is false. In all other cases, the statement is true. So that is what I mean with that. So P implies Q only means this. So P implies Q does not mean that when P is false, Q is false. That is not implied by that. And when we write that something X is an element of A implies that X is an element of B, we are not implying that X is an element of B because there is some mechanism relating these two things. We are not implying that. If you do that, you may suffer injury. When you say that, we are implying that the suffering and injury is actually due to the wrongdoing, that particular. There is some relation between that. There is also implied in an ordinary statement like that. If you do that, it may cause some injury. If you drink water from that source, you may get diarrhea. We are implying that there is some bacteria in that water and it may cause diarrhea. But mathematically, when we say that P implies Q, we are not bothered about such things. We are only saying that when P is true, then Q is true. This is a statement only about the truth value. There may not be any relation between these two statements, P and Q. I think this is philosophically important. So P implies Q should be understood in that way. The statements P and Q need not have any relation. For example, I can write if 1 is equal to 2, then a circle is a square. I am writing if 1 is equal to 2, then a circle is a square. Here, what is the truth value of the statement 1 is equal to 2? 1 is not equal to 2. So the truth value is equal to is false. It's false. And circle is a square is also false. Circle can never be a square. So the truth value of this statement is false. Truth value of this statement is also false. And therefore, when you look at this, you can see that the statement is true. So this statement is true. But this does not mean that circle is square because of this. These two things are completely unrelated. Of course, both are wrong, but both are unrelated also.